When we look at the world, we see all the different phases of matter. We see solid, liquid, and gas. We also notice that we can change one phase to another either by adding heat or taking heat away. Typically, the main substance that we see change phase is water, but in this picture we see that iron can also be made into a liquid if you have a high enough temperature. Some things are solids at room temperature, like iodine. Other things are liquid, like water, or in this case, bromine. So this raises the question, what is it that determines whether or not a substance is a solid, liquid, or a gas? Which is really just another way of saying what accounts for the difference in boiling point and melting point between different substances. So in order to answer that question, we're going to take a look at what's referred to as intermolecular force or intermolecular attraction. And we've already talked previously in some detail about bonding. We know that bonding occurs between atoms when there's a sharing of a pair of electrons or more than one pair of electrons. But we can also have what's referred to as intermolecular attractions. And in this particular case, what we're talking about is between one molecule and another. So in this drawing here, it's the dotted lines. These dotted blue lines represent an attraction. It's weaker than a bond, but it's still an attraction. So we're going to take a look at the three main types of intermolecular forces. So we have dipole-dipole, hydrogen bonding, which is really a special case of dipole-dipole, and then finally London dispersion forces. One point that I will make right now is that in all cases, the intramolecular bonds, in other words, the typical covalent bonds, are much stronger than the intermolecular forces or attractions. So the first type we'll look at is called dipole-dipole, and in order to have dipole-dipole attraction, you have to have a polar molecule, which we've talked about before. So with a polar molecule, we have a positive side of the molecule and a negative side of the molecule, and then the attraction is between the negative of one side, the negative pole, and the positive pole of the other side. And the strength of this dipole-dipole attraction is dependent on the dipole moment, and the dipole moment is dependent on the difference in electronegativity between the two elements involved. So the greater the difference in electronegativity, the greater the dipole moment, and therefore the dipole-dipole interaction will be greater. So a particular example or a subset of dipole-dipole attraction is the hydrogen bond. And hydrogen bonding takes place when you have one of the three elements, nitrogen, oxygen, or fluorine. Also, the hydrogen has to bond to a lone pair of electrons, which means that the nitrogen, oxygen, or fluorine must have at least one lone pair, one unshared pair of electrons. And again, down here, there's the attraction that we're talking about. And this is a little bit larger example of the same thing. So you see, for example, with water, if we just focus, let's say, on this water molecule, that you can have two molecules here that it's attracted to. So these would be two different molecules. And then on this side, also you can have another two. So it makes a pretty powerful bond there. So it's one of the stronger types of intermolecular attractions. The last type is referred to as a London dispersion force, and this is an instantaneous dipole, and what happens is you temporarily have an imbalance in the charge, just a statistical occurrence, and when you have a more negative charge on one side of the molecule, it affects the electrons on an adjacent molecule. So if you look at this picture, you can see what happens here. So the blue represents a nonpolar molecule. So this might be something like N2, for example. And then what happens is just, again, statistically, there's a fluctuation and you get a negative side of one molecule and a positive side of the molecule. Let's say, for example, again, that this is maybe I2. So you'd have more negative charge there and more positive. And then what happens is that causes an adjacent molecule to also become unbalanced as far as the charge. So that's referred to, like this one is referred to as an induced dipole. So this is an instantaneous dipole, an induced dipole, and this would just be a typical nonpolar example of the molecule. The general idea is that the stronger the intermolecular force is, the higher the melting and boiling point. And the reason for that is that when you melt something or you boil something, you're breaking the attractions between molecules. If we look at this chart, this is kind of interesting. So you can see four different series taking place here. So you can see the one with carbon. So this is group 4A, and you can see the gradual increase of the boiling point as we move across. When we go to the series for nitrogen and fluorine and oxygen, we see a very different pattern. We see that the first one in the series is much higher, has a much higher boiling point, and then it drops down. And we would attribute this to the hydrogen bonding, which is very strong. Down here, the increase was just the increase in dispersion force. And if you look from H2S to H2E to H2TE, that's the same sort of pattern. The main difference between those is the difference in the number of electrons and the intermolecular force.